So we've talked about distributions. How do we visualize distributions or frequencies? And now let's look at how do we look at the relationship between two numeric variables. And this could be a numeric feature in the label or two numeric features. And our main tool for doing that, which is what I have the code on the screen for, is a scatter plot. And so, again, this shouldn't be too surprising. The structure here, it's very similar to what we've been doing. Define a figure, define an axis, and I'm going to use the pandas from the data frame. I'm going to use the pandas.plot.scatter method. And I'm going to set x to whatever column I want to plot. And y, you see I've set y, my default is price. So I'm going to look at these 4 numeric features versus price. So that's why I'm looping over 4 numeric features here. And as always, very important, I have my labels for my axes and chart so that I know what I'm looking at. So my first plot is curb weight versus price. Well, it makes sense, right, that heavier cars probably cost more. You can see there's just generally a trend here. But we also see some interesting structure. This group of cars doesn't seem to follow the trend of this main group. In fact, we have some rather mid-range and weight cars that are quite expensive. So that's interesting. We need to investigate that. When you're doing data exploration, those are the things you should be looking at and thinking about, gee, why is that? Why would these relatively mid-weight cars be so much more expensive than, say, all the other cars in that weight range? And why in general are these very heavy cars also at sort of off the trend line of this? And you start getting different views. It's very important in exploring data to understand different views of the data. So we've got the same kind of plot here, but this one is engine size. And again, we've got a trend, but there are some oddballs. We've got these cars with very small engines here that seem to be not really on the trend. And we've got these cars with very large engines over here that are also off by themselves. So again, we need to investigate this. Why do we have some really large engine cars and some really tiny engine cars? And that there might be a reason for that, and it might affect our modeling. And we can do the same thing with horsepower. It's a little simpler here, but there is still one outlier, maybe a few others. And city miles per gallon. So now we start to see, we have this bulk of cars here, but then we have this group of cars that seem to be more expensive for a given fuel economy. We have this group of cars that stands out from any trend down here. And we have these 3 cars that are very high fuel efficiency and quite inexpensive, but they're definitely off the trend. So we've learned quite a bit about that there's some interesting things going on here with the data on these cars and their characteristics versus their price. So if we're trying to predict price, we really need to understand some of these details. But there's a problem here, and it's called overplotting. If you look at these regions like here and maybe here and here, I cannot tell how many points are lying on top of one another, and I doubt you can either. It's clear there's a lot of cars within a certain narrow price and fuel economy range. And these must be ranges that are attractive to manufacturers, but we can't really tell the density of those plots in any way. So what can we do about that? And there are different methods to deal with overplotting. Our first tool to deal with overplotting is called transparency. And we can set a parameter. Alpha is actually the inverse of transparency. So alpha equals 1 is perfectly opaque. Alpha equals 0 is perfectly transparent. So we're going to use a fairly low value of alpha, so high value of transparency of 0.2. So you see the code here is just the same as it was before, except I've added one more argument to my call to the pandas.plot.scatter, which is an alpha argument. All right, and we're going to make that plot. And I'm going to go down to the bottom here and just show you the results. So now you start to see, well, you can still see, they look a little fuzzier, but you can still see the cases where the cars are just one on one. And then you can start to see there's still some overplotting, but you start to see where the high density areas are much better, like here especially, and maybe a little bit over here and here. So transparency, if you don't have severe overplotting, generally for small to medium-sized data sets like this, using transparency can be an effective way to deal with overplotting. But imagine we had, instead of 195 autos in our data set, maybe we had 100,000 autos in our data set. Well, then we need a different method. And there's two choices here. There's a kernel density estimate plot. Recall when we did one-dimensional frequency distributions, we used a KDE, a kernel density estimate plot. Well, there's a 2D version of that in Seaborn called and it's part of the joint plot method. And we're just going to use that with our same columns that we've been doing. And I'll show you what happens. So first off, what is a joint plot? Well, the joint plot shows the kernel density estimate of curb weight, which is on the horizontal axis, and price, which is on the vertical axis, as the margins. So those are the marginal densities or marginal distributions of this price versus curb weight. And then you get this nice kind of contour plot, almost like a topographic map. And you can see that, yeah, just as we suspected, maybe around 30, a curb weight a little over 2,000, and a price of maybe 9,000 or 8,000 or so. There's kind of this spot where a lot of manufacturers are building cars of many different models. That must be an area that consumers are interested in. So that's an important observation. Likewise, for price versus engine size, we see that, remember there were these very large engine cars, but they're very diffuse. The majority of cars have an engine around 100 cubic inches in this case, and a price around the mode of price. And you start to see why you get this distribution of price too, because you just have a lot of cars that have a similar engine characteristic and a similar price, and that's leading to this and that density function. So you start to, by creating these different views, you unravel what's going on. And remember, city miles per gallon was pretty diffused. But again, there's kind of two modes maybe. There's a lot of cars in the high 20 to 30 miles per gallon. And again, they're all in that fairly low price range. So that's one method of looking for dealing with high levels of overplotting. The other is a hex bin plot. And hex bin plots, contour plotting is fairly computationally intensive because you actually have to build this grid and do the contour algorithm over it. Hex bin plotting is like the two-dimensional equivalent of a histogram. So you simply are binning the values into hexagonal shaped bins. And we use hexagonal shaped bins because they pack in 2D. So let me run that and you'll get the point. And again, get the marginal density. Now the marginal density is shown in the form of a histogram. And you can see where the highest density of cars are right there. Like, say, curb weight of about 28 or 2,700 and a price of about 8,000 or 9,000. And the other nice thing about the KDE is even if there's just one car in the cell, it still has some color to it. So whereas the contour plot kind of lost some of those outlying values, you just don't see them very well. In this case, you definitely do. And so I like the KDE plots once you get used to looking at them. And you can see how they really are like a two-dimensional histogram. And in fact, you can, as I already pointed out, you can see the one-dimensional histograms on the margins of this joint plot. So that's very nice. And finally, if we go down to city miles per gallon versus price, you see there's a number of bins with a fair number of members. And then there is this other area where there's a fair number of cars too. So those are some powerful methods for looking at the relationships between numeric variables. We looked at scatter plots, and then we dealt with overplotting by three different approaches. One was using transparency of the points, kernel density estimate contour plots, and the hex bin plots, which are the 2D equivalent of a histogram.